And in this lecture number 6 of the basics of microwave propagation, we will learn about something. Because my idea is that first I will give you some kind of foundation from where you will start to learn things. Because we can say that if you know something what is going on behind the scene, because the tool is very powerful and it can give you almost everything. You don't need to know or learn anything. But as we know about a lot of other tools as well, that if you know the behind the scenes, I mean, how things are being done, how the calculation, you don't have to be a mathematical expert. I mean, you don't have to be an expert in physics because some of these things are quite, they need some kind of elaboration. You need to learn them very well. But at least if you know some part of it, if you understand at least some part of it, that how this all is going on, then it will make your life easy. I mean, when you are dealing with a link, you have some idea that, okay, when this happens, for example, if you are troubleshooting a link, you know that what kind of things affect the link. You know that very well because you have some background idea. So I will try to make a foundation, just like I'm trying to make a foundation from last 5 lectures. In every lecture, we are learning something very small, but it is kind of a foundation. Like in the previous lecture, the last lecture number 5, like we learned that basically whatever else happens, but to baseline a link, we have to know that what is the receive level, because then we can baseline, I mean, because we know that what is the thing that we can achieve. I mean, you are sending 10 dB and you are receiving minus 70 dB. Okay, that's fine. Now how you can keep it, I mean, how you can keep it as it is. So in this lecture, we will know that how you know that if you are sending 10 dB, then you will receive, for example, minus 70 dB, how you will receive it. Why not something else? What things are the constituents of it? I mean, how this receive level is made. So the major part of the receive level comes because of the free space loss. It is the maximum loss that your signal takes. It can, again, it's a baseline loss. It can increase and decrease based on different things. But for a general consideration, for a baselining, when we send a signal, then what we receive here, I mean, I send something from here, but what I am receiving here in this antenna, this is important. So whatever is lost in between, we can calculate it through the free space loss. So let's go in it. Let's try to deep dive and learn that how we came to this value. So the free space loss is a predictable thing and it is given by this formula. FSL is free space loss, and this is very simple. 92.4, it's a constant value, plus 20 log of t plus 20 log of f. So now today, I mean, you can use this formula in any path loss or any software, and you will be, I mean, it will be a kind of new learning. At, like, you know, when you're getting a number on the path loss, and now you can verify that number through mathematics as well. But we will go in a further small detail. I mean, I will not go in too much detail, but at least I will go in a small detail so that I can just show you that why it is dependent on the distance and frequency. I mean, there should be some reason. I will go up to one level only, not too much in detail, but at least you will have to have some idea. So free space loss is 92.4 plus 20 log of t plus 20 log of f. D is the distance. It should be in kilometers. If the distance is in miles, then this constant changes. It changes to some other value. That also we will learn from how we will go ahead, and we will see that the detail of this. Similarly, this F should be in gigahertz. So we will see that why it should be in gigahertz. So I have some small quiz type of questions, because when you will be going through this, some questions should come to your mind. I mean, that as we saw that the free space loss looks to be more lossy at higher frequency. Like if you see, this is a frequency component. If we will increase this component, the total loss will also increase. But my question is that why? Why on high frequency we have a higher loss? Why not it is reversed? So you should just think about it. I mean, that what comes to your mind? I mean, what do you think? And if you can give me some comments on that. Also, if we double the frequency, we know that signal will either increase or decrease. We know that it will increase. I mean, because of this first question, we know that when the frequency increases, the loss increase. But if you just double the frequency, what will be the effect? I mean, how much dB loss will increase? So this kind of question should come to your mind, and when you will be planning links, when you will answer this question and you will make it a part of your learning, so it will help you in planning. When you are doing something, you know that if you are shifting a site, how much you shift and how much, what will be the kind of impact. I mean, so you will learn something when you will start questioning, when you will start thinking about it. So these are just two questions to make you think about the free space loss equation. So now we will come to the mathematical part of it. And as I said that I will not go in too much detail, but at least I will go in some of the detail. I mean, I will not leave it very simple for you, but I will not make it very hard as well. We will just go up to some value. I will leave something for you to learn. And so let's start. I mean, so for example, we are transmitting some power PT, power transmit power PT. So a transmitter is transmitting it, but the transmitter is transmitting it through some isotropic antenna. Isotropic antenna is a kind of antenna which is transmitting in all the directions. Just to clarify this one thing, because this is very important. When we will go in the next lecture I will show you the full equation, because free space loss is basically a part of equation. When we are trying to get the receive signal level which will be received by the antenna, then free space loss is one component in it. It is not the full thing. We have some other components also that I will discuss in my next video. But here this thing is a bit important, that right now we are assuming that there's an isotropic antenna. I mean, there's a this antenna is like a single wire. I mean, it's an open kind of wire, and it's transmitting in all the directions. So if the antenna is here, it's transmitting in this whole area. I mean, at you get everything. Like from here we start to transmit, and then it uh, just like the light. I mean, it expands. I mean, it's expand with the distance. As you are sending light from one source, you know that the light expands. I mean, so in the same way, when we transmit power, it starts from very small and then it expands like that, and then it reaches the whole area. So the isotropic antenna basically transmits in all directions, but as the receive antenna is in some particular direction. So from here the power is expanding in all direction, but some part of it is reaching here. So we will be interested to know this part which is reaching the receive antenna. But to know this part, we have to know that how much generally power is being spread, or what is the power density at some distance from the, like from here you are transmitting. So as far as you go, we see that, as I told you, that this expands. I mean, so it means that as far as you go, the power density decreases basically, because the power is expanding. So it means the density is going low. At the transmitter part, the density is too much high, and then the density starts becoming low and low and low. So when you reach to some distance, the density is basically transmit power divided by 4 pi d square. So you see that it is being divided by the frequency. So divided by the distance. So power flux density is getting low by low by low as far as you go. I hope this point is a bit clear to you. If this is not very clear, it's not any big problem if you at least get some idea of what is being talked here. Because as I told you that it is not a physics or math class, I don't want you to learn it very well, but I just want to have you some idea of it. So as we know that it's a density. So density is basically something per square volume or per square area. So this is power density. So it is denoted by S, and this is equal to power transmitted divided by 4 pi d square, where d is the distance between the transmitter and the receiver. This is the distance d. So at some specific distance, we have some value of s. At another distance, the value of s goes down, but we have a different value of s. Now the transmission loss depends on how much power is captured. As I was telling you that this power is expanding. So it expands, and for example it becomes this much. But for example your antenna is very small, this size. So even though this whole power is available, but you are receiving some part of it. So the received power is basically power density multiplied by the area of the receiver. So as we know that this is a receiver, it should have some area. So this area is too much dependent. I mean, how much area, that's why if you are working in the field, you know that the bigger antenna has a high gain and a smaller antenna has a lower gain. So the area is very important, that how much you are receiving, how much area is being received. So let's go further. So if we are using a hypothetical isotropic receiving antenna area, now, just as I told you that, for example, we are sending it from isotropic antenna. So for this, we are receiving also an isotropic antenna. And this isotropic antenna, the area is very much dependent on the wavelength of the signal. Now again, if you are from physics, you know that voltage standing wave ratio kind of thing and how these dipoles antenna work. So you know that the antenna which is receiving, if its antenna size is not as per the wavelength, then you don't receive the maximum power. So the antenna which is receiving, it should also be constituent of the wavelength. And this wavelength, lambda, you know that this wavelength is basically, it has a frequency component. Wavelength is calculated from the speed of light and the frequency of being what is being transmitted. So the free space loss as itself, I mean the free space path loss, as we know that any loss between a transmit and receive is basically a ratio of how much you transmit and how much you receive. So the ratio of transmit power to receive power. And this lambda is basically because as we are working with frequencies, we are not working with the wavelength. So we will change it to a frequency component, and lambda is equal to c over f. So now this is so we know this is the receive power PR, and this is the transmit power. The transmit power is basically they are, because these two are connected to each other through this S. If we put PR here and in place of S, we put this value PT AR oblique 4 pi D square, and then we make this AR in its own value like lambda square oblique 4 pi, and we just substitute everything, then we can come to this equation. Now to make you some kind of I mean, I don't want to go in very much detail, even though I could fully, I mean, I could show you exactly how it is done, but here LP loss is PT oblique PR, and you need to use this equation number 3 and put other values in it, like the value of S and AR. So you will reach this point. If anyone is having any issue and he wants to go in a bit of detail that how we reach to this point, then I can very easily help him. But again, my point should be that if you really want to learn, then try to do something by yourself as well. This is not a very difficult math. It is very simple math. I mean, you just have to substitute some values and you will reach this value. Just remember that this loss is basically power transmitted by power received. This is the loss. You just have to get these two values somehow. And how they will come? You have to use this formula. In this formula, you have to put the value of S from here and value of AR from here. And then you will have a PR here and a PT here. And then you just have to rearrange these and you will come to this point. It is very simple. But again, if anyone is having any issue, then I can show him the steps which were used to make this. So now there is a bit of more suspense, more just to make it more. I don't know, maybe some of you may not like it because if you are not very good in math and physics, then maybe you will feel a kind of boring that, okay, what is this going on? Where the things are coming and going. But when we start with this free space loss equation. But when we end on this equation. So anyone can say that, I mean, what is this? I mean, how these, I mean, you said that free space loss is this, but now you are saying that loss is this. So what is? So basically, when we use the microwave analogies and everything, when we use the power is here, it will give you simple power, like in power in wattage. But in the free space loss, you know that we have power in dBs. We don't have the absolute power, we have relative power. So just to give you some idea that how these two converge to each other. First, I was thinking that I will leave it to you as a kind of quiz, like the name also suggests. And then I will say that, okay, goodbye. I hope you can converge these two. But then I thought, no, it is not my style as well. I don't want to leave you in kind of this kind of problem. I will try to solve it a bit only, not too much, but a bit only. This LP, which is basically, as I told you, this is the absolute power, but we don't use absolute powers in our calculations. We use relative powers. So this LP is connected to this FSL through one single thing, 10 log. So FSL is equal to 10 log of LP. So now you know that these two are now connected. So same we will do here with everything. This will become 10 log of 4 pi oblique c ka whole square. And when we take logs, then the multiplications changes to additions. This will be 10 log of f square plus 10 log of t square. When there are squares, then the squares, I mean, this 2 is basically multiplied from the log value. It comes out of it and it's multiplied here. So this will become 20 log of 4 pi oblique c plus 20 log of f plus 20 log of d. So you can see that this is the same value, 20 log of t. This is the same value, 20 log of f, which means that this value, when you will solve it, it will come as this one. And how is this will be done? Then again, I leave it to you. I mean, at least you should try to solve this small part. I mean, how this all becomes 20 log of something. So I hope that you could at least you can solve this small part. And from here we learn one more thing. For example, we know that log of 10 is 1 and log. So if we assume that if there is a link where the distance is 10 kilometer and frequency is 10 gigahertz, then because log of 10 is 1. So for this peculiar link, which is 10 kilometer and 10 gigahertz, this will become 92.4 plus 20 plus 20. So your total loss will be 132.4. Like for example, if you are sending 0 dB, for example, if Tx is equal to 0, then your Rx will be minus 132.4. Just to give you an idea that for some values, I mean, how we calculate, I mean. So for a specific value of 10, because log of 10 is 1, it becomes very simple. I mean, that these values are just solved like 20 and 20, and you just add it. But for other values, you have to calculate the logarithmic value of that frequency and that component. So I hope that this was not too much, but this was not too less as well. And even though I tried to answer a lot of things, but still because my personally, I like to put some questions in your mind so that you think about it and you ask those questions and then we collectively work on it. So anyone who is watching this video, if you find that, okay, there's some question and you need to understand it somehow, you have some more questions on it, you can ask it, you can make a comment and I will respond to that. But if it was very simple for you, easy peasy, and you understand everything, then that is great. But I hope that for some of you it should be very nice. For some of you it should be a bit boring or a bit difficult. But I think this is life. This is our journey of life. So let's meet in next video where I will take you one step further that okay, we have the free space loss, but how to calculate now the actual receive signal level, which is called RSL. It is different from free space loss. Free space loss is just a part of it. So hang on, keep connected, keep watching my videos. If you like it, then share it with your friends as well. So hope to see you in my next video. Goodbye.